today I hope to, I'll start by giving you a bit of an introduction to RISC-V, what it is, why you should be interested. I'll talk a bit about where RISC-V is in terms of status, pick off some topics which I think are relevant to a software audience, giving a taster of the sort of discussions which are ongoing in that community right now, the controversies, things which are actively in development, and then look ahead to the future and what's maybe on the cards, what opportunities there might be for doing something different with open standards and open instruction sets. So, how many people here have heard of RISC-V before, or had something? Basically everybody, but some exceptions. So I'm going to give a brief introduction to what RISC-V is. So first of all, RISC-V is it's an open standard of an instruction set architecture. What is an ISA? Well, that is effectively the interface between software and hardware. So this is the encoding of instructions, the semantics of those instructions, and I mean, to be honest, a whole bunch of other stuff that goes with it as well, such as memory model and things of that nature. So in comparison to something like ARM or MIPS or x86, RISC-V is an open standard, meaning that anybody is free to implement it, and beyond that, it has a somewhat open development model. So this is managed by a not-for-profit which was set up to manage the evolution of RISC-V, the RISC-V Foundation, which has members including Google, Qualcomm, Microsemi, NVIDIA, NXP, a whole variety of other companies. And one thing I should make clear is that I'll be talking quite a lot today about open implementations or open source implementations of hardware and reference designs, but that isn't a necessary property of RISC-V. Many of us are interested because we're interested in open source as it applies to hardware, but there's nothing about RISC-V which requires an open source implementation. In fact, it's a very conscious decision that the RISC-V Foundation is set up to support both proprietary and open implementations. Now, another aspect of RISC-V which differs versus some of the other more established proprietary instruction sets is that it sets up to allow and in fact encourage custom extension. So if I go and get a license, purchase a license to build, say, an ARM processor, even if I get an architectural license, which companies like Broadcom or Qualcomm or Samsung have, which allows me to do my own implementation of the ARM instruction set, I don't also have the ability to add my own custom instructions. That's ultimately something where ARM will get feedback from their customers, and then a future revision of the ISA might add new instructions, but it's not something which individual licensees have the ability to add if there's a particular, which we might want to do if there's perhaps a new security feature which you want to implement, or as a acceleration for a particular use case where you want to add in customized instructions. Now, there are other ways of getting that acceleration, of course, through more tightly coupled accelerators that are off-core, but extending the instruction set itself is off-limits. Now, as I mentioned, RISC-V has a open-ish development process, so you have to be a member of the RISC-V Foundation to take part in some of the development discussions. This is relatively low cost. I think the minimum entry is around $5,000 for per annum for companies, and then free for active open source developers, or otherwise $100 for individuals. And it's, I'm not going to paint a picture to say that it's everything works fantastically off the bat. Open source development and open collaboration is a difficult problem. It's not all rainbows and unicorns from day one, but it's, I think, already proven successful in a number of cases. So the work on the standard for the memory model is a particular example of something which has been, I think, a real success story of people across industry and academia working together. When the initial RISC-V, RISC-V itself came from UC Berkeley, so it was based on a series of academic projects. It's called RISC-V because it's actually the 5th iteration of a RISC-style architecture that they'd worked on, and ultimately they decided that it was worth putting the extra effort into documenting this, reviewing all the design decisions, and then sharing more widely, as it seems almost a sort of bizarre situation where up to now almost every other sort of interface which we interact with is an open standard in some way. So from HTTP, SQL, through to even external interfaces on our hardware, such as USB, but this fundamental interface between hardware and software has remained something which is non-standard and not free to implement. And with the RISC-V instruction set architecture itself, I'll go through some of the technical design decisions, but actually, and this is a good thing to say about any ISA, it's fairly boring. It doesn't go for particularly quirky or interesting design decisions. 64-bit, 32-bit ISAs, RISC ISAs have been around for decades now. There's a huge wealth of knowledge on how to build them. That knowledge has been applied through good engineering work in order to produce the RISC-V standards, but there's nothing, particularly about the user level ISA, the stuff which your user space will be executing, which is particularly, novel beyond the fact that it's open, standard, and increasingly well supported by industrial partners, software, and that sort of thing. Now, a key aim of RISC-V is scalability. So it aims to be an ISA which will scale all the way up to high-performance computing or rack scale computing, all the way down to deeply embedded devices with no MMU, use cases even smaller than individual microcontrollers. So an ISA which might be a small core which is deeply embedded in some IP block on a much larger SoC design. And this is actually a real problem and something which has attracted, I guess, initially companies like AMD to RISC-V. I think in one of the early RISC-V developer meetings, someone from AMD put their hands up and said the reason they were interested was because that when they ship a AMD processor, a recent one had 15 different ISAs on it. And this is because that every piece of IP that you integrate, so your sound module, the power on management, whatever AMD's equivalent of the management engine is, these all tend to implement different ISAs, and they're somewhat hidden to the user. And of course, this is something of a nightmare in terms of maintaining different compiler tool chains and that sort of thing. And the RISC-V approach in general is that if the standard solutions don't work for you, that's fine. You can add your own extensions, and there's great care has been done to ensure that there's a large amount of encoding space for defining those custom extensions. This flexibility can, of course, be a disadvantage. As Justin mentioned, I spend a lot of my time with compiler development. I'm the primary author and upstream maintainer of the RISC-V backend for LVM. And one of the challenges is, of course, that RISC-V is such a varied architecture. So it's structured so that you're split into this series of base ISAs, and then there are a series of standard extensions which layer on different functionality. Say the MAFDC, which is multiply, atomics, single precision floating point, double precision floating point, and the compressed instruction set. And so if you hear people talking about RISC-V, they'll quite quickly start talking in these very opaque little sequences, these isostrings, which is kind of weird, I'll admit, but you do get used to it. So RISC-V, so I mentioned the base ISAs. I guess the main ones to worry about are RV32I and RV64I. So these are the integer-only subsets of the 32-bit RISC-V ISA, so the version where registers are each 32-bit in width, and the 64-bit ISA, where the registers are 64-bit in width. And these may be implemented in systems which have a MMU, TLB, and a full virtual memory system, so capable of running Linux, or as I said before, something which is much, much smaller and lighter weight. There's also a compressed instruction set. This is the C extension I mentioned before. It's actually a variable width instruction set in that you can have a mix of 16, 30, in the standard ISA, 16 and 32-bit instructions. If you have custom extensions, you can actually go to 48-bit or 64-bit instructions, giving you a pretty huge encoding space for custom additions. Now, an interesting aspect of it, particularly for what we're talking about today in terms of interesting directions for operating system design of RISC-V is the split of the privileged versus unprivileged ISA. And there's been some argument in the RISC-V community about, so arguably other ISAs don't have such a clean split. Arguably due to, I guess, pragmatics and real-world problems, the RISC-V split isn't completely clean, but at least as much as possible, there's a split between the user-level ISA, so the definition of the semantics of instructions, ignoring support for running operating systems, concerns such as handling interrupts and exceptions, and support for virtual memory, or other machine-level control status registers, which you might use to customize handling of traps and that sort of thing. And then the privileged ISA, which defines all of those things and defines the standard, at least standard interface is sufficient to, for instance, boot a FreeBSD or Linux kernel. And of course, beyond the ISA, there's a whole bunch of standards which you would start to care about. And some of these come under the purview of the RISC-V Foundation, others do not. And I guess an example would be the debug specification, so specifying what you need to do in order to hook up GDB via JTAG to your RISC-V implementation. One which is kind of on the border is the interrupt controller specification. Those who are familiar with ARM in its earlier days, that suffered from a proliferation of different interrupt controllers. There's an attempt to specify a standard interrupt controller for RISC-V, which now become 2 standard interrupt controllers, but these are these are all opt-in. So it's and in fact so is the privileged ISA itself. So you could the privileged ISA as currently specified with RISC-V is just like the base user level ISA, trying to be pretty boring, just providing sensible support for running modern operating systems. If you want to do something which is much more novel or more interesting and goes beyond, I guess, the current interfaces which people tend to be using, then you're totally free to take the standard unprivileged ISA and get hopefully full compatibility with compiler toolchains and user-level software compiled towards a standard operating system API, but then go and do completely your own thing on the privileged side. Now, to give a little bit of background, I'm not quite sure what familiarity people have with hardware and FPGAs, so I thought I'd just take a couple of minutes to talk about, just to define terms, which I'll probably be referring to later on in the talk. So an FPGA is a field programmable gate array. It's effectively programmable hardware. So you buy one of these boards. This is a Nexus A7 sold by Digilent. This one costs a bit under $300, and this is sufficient to. You'll then take your hardware implementation, say written in Verilog, which is a hardware description language. You'll put it through the somewhat clunky FPGA synthesis tools. That will spit out a bit stream. You then put that bit stream onto your FPGA, and that bit stream could, for instance, be implementing a RISC-V core capable of running Linux. So through low risk, we have a FPGA-ready distribution of RISC-V core plus associated SoC peripherals, which runs at 50 megahertz on one of these Nexus boards, which is clearly more than an order of magnitude slower than a custom ASIC, so a custom chip. But on the other hand, it's something which you can very rapidly iterate on. You can, it might take half an hour to run through the FPGA tools, but then you get it back versus obviously the huge cost and very, very long lead times of producing a chip. And of course, at 50 megahertz, it's actually quite, it's not unusable for Linux, but actually a pretty reasonable speed for anybody doing microcontroller-based systems, running FreeRTOS and that sort of thing. It's actually not that different to a microcontroller chip, and other than cost, which is substantially different, but in terms of performance, roughly similar. Now, so I mentioned one of the key advantages of working with an FPGA is this rapid iteration time. It's also useful in order to start to get some sort of performance numbers. So you can have a effectively real hardware implementation. You could map it to FPGA and get some numbers out of it. It is easy to get somewhat misleading numbers. So I'll talk a little bit later in this about a virtual memory optimization, which was explored using RISC-V, using a open source RISC-V implementation as a base. If you just naively take performance numbers from an FPGA, you are liable to get slightly misleading results, because the memory interface, so a DDR controller, that's a hardened piece of logic that's running at effectively full speed. So that's running fast, whereas your core is running relatively slow, 50 megahertz. And so the ratio between your core performance and your memory performance is somewhat off. So your L2 cache misses are going to be much, much cheaper in relative terms versus a real ASIC. And this is something which can, even in the published literature, it can trip people up quite a lot, as it's not actually trivial to work around unless you actually produce or implement a simulated memory controller, which is simulating the sort of optimizations that a memory controller is doing. But of course, before you go through all that, it remains an incredibly useful thing to do to modify a software simulator, a QEMU, Gem5, or something similar. In terms of producing ASICs, so producing real chips, for people who aren't familiar with semiconductor economics, effectively it's you have two choices. You can produce a very small number, so tens to maybe 100. You typically do this via a multi-project wafer. So as you may recall, semiconductor manufacture is a lithographic process. So on a multi-project wafer, this is an intermediary will collect together sort of test designs from a whole bunch of different research groups or companies, stick them all on the same mask, and then they'll produce some wafers of that, dice them up, ship them back to you. And that, economically, that only produces, say, 10 to 100 parts. But that, of course, is very useful, because you might spend $100,000 to get these test chips back before you then spend multiple millions of dollars on a mask for a full volume run. And so the issue is that when you then go to the full volume run, you're buying an entire mask for yourself, which is your design stamped out many, many times. And the only economic, it is only really economic when you're producing millions of chips. So there's this quite difficult ground on the sort of in-between, which is definitely one of the real barriers for open source hardware. In that it's quite difficult to go from a point of something which a tiny community of people to access to something which a slightly larger community of people to access. It's kind of go big or go home. And in terms of semiconductor licensing, I mentioned ARM, and MIPS has a similar model. If you want, for instruction set architectures and core designs which are licensable, it typically works where you would talk to a company, you would pay an initial upfront fee, and then pay royalties based on the number of chips that you produce and sell. And this is, and that might be the same with RISC-V, depending on the company you're speaking to. But I think most companies, even those with proprietary implementations, are going for very low upfront costs, and either just upfront costs and no royalties, or very low upfront costs and then some royalties. But of course, if you're taking a fully open implementation, then there's no upfront costs, no royalties. You can stamp out a design or a modified version of a design as many times as you want without worrying about increasing your licensing fee. So RISC-V it's now been going for, around 4 years or so since the public announcement. So Berkeley released it to the world. The original developers of RISC-V then produced a VC-backed startup, Sci5, which has been doing a lot of work in the RISC-V ecosystem, but there's also a number of other vendors who are producing cores and producing tooling around it. On the compiler side, GCC support is upstream. As I mentioned, I'm primarily pushing the work on the RISC-V backend for LLVM and support for Clang. Support for that is upstream for a large portion of, a large portion of the RISC-V variants which we need to support and is under active development. glibc is upstream. Muzzle, there's a downstream port which should hopefully be upstream soon. There are initial Rust ports based on the LLVM work I did for bare metal toolchains, though Linux is blocked on the next stage of LLVM development. There's also some Go support, which stalled for a while, but I believe has now sort of picked up again. I mentioned that simulation is a popular way to get started. So although it's great that you can modify a hardware, a real Verilog implementation of a RISC-V core of interest, is clearly much more productive to get started with to modify a higher level, easy to modify software representation. And so there are choices such as QEMU, Gem5, what's become the de facto reference implementation of RISC-V or reference software model is Spike, which came from UC Berkeley. There's also TinyMU, which is a nice project, which is worth mentioning as that was written by Fabrice Bellard of QEMU and FFmpeg fame. In terms of available hardware, there's Sci5 produce development boards on the Linux-capable side, the Freedom Unleashed. There's a microcontroller class development board. There's also a Kendryte board from a Chinese manufacturer. More recently, NXP have started this OpenISA effort, which has a development board available which has a pulp microcontroller on it. And then there are FPGA-ready distributions like the one which we publish at Low Risk. And in terms of open source implementations, the two major sources of cores are Rocket, supported by UC Berkeley and Sci5, and Pulp from ETH Zurich, which now includes a variety of cores, so on the microcontroller side, but also on the Linux-capable side, a design called Ariane. On the operating system side, there's support for at least FreeRTOS, Zephyr, SEL4, interesting to some initial work on TOC. So I mentioned, TOC, for people who haven't encountered it before, is a really interesting RTOS implemented using Rust. And there's some initial work on that targeting RISC-V based on the Rust RISC-V LVM toolchain. It has a number of interesting aspects to it. It makes good use of Rust's memory safety, and also has a model for loading applications in your RTOS, which typically whereas more usually it's all be compiled into a single binary and it's all fixed at compile time. Linux and FreeBSD support is upstream and well developed. There's also on the more experimental side, there's Harvey OS, which is a modern reimagining of Plan 9, and Helen OS ports also available. There was a talk about the Helen OS work at FOSDEM recently. We have a series of bootloaders available. I'll say a little bit more about BBL and OpenSBI later, as that touches on a interesting topic in the RISC-V community. There's also been sustained and active work, particularly on Debian and Fedora. So large portions of the Linux base system for both distributions is compiled and working. I'm actually a blocker in a sense on the LVM side, as Rust has become a quite key dependency for compiling a modern Linux system, with libraries such as librsvg being rewritten in Rust. And so they're kind of, in both cases, they're using an older version of librsvg before it was ported to Rust, while they await upstream LVM support for Linux binaries. And I've thrown up a large quote here, and you're going to be very tempted to read it, but I'm just trying to pick up on something I really like about the RISC-V specifications, which is for most of the major design choices, if you wonder why a decision was made, there are these really nice little asides which explain exactly what was considered and what went into that decision and why they went that way. So page sizes is one, which remains a slightly controversial topic. Some people feel that 4 kilobytes pages are a little bit old hat, but if you want to revisit the initial discussions, there's a nice little aside in the RISC-V privilege spec. There are similar asides on actually most design decisions, like on the user level spec side. There's a good explanation of why RISC-V doesn't support conditional move, even though ARM, AArch64, Power, x86, and most other current ISAs went with that choice. Now, I wanted to pick up on a few topics that I thought would be particularly relevant to this audience. And the first one I hinted at before, which was this issue of the SBI, or Supervisor Binary Interface. And this is this really goes back to this idea of separating the user and privilege level ISAs. So in RISC-V, there's not just 2 privilege levels. There's, at least on a Linux-capable system, you tend to have at least 3. So you have machine mode, which is the most privileged level. Code running at that, running with that privilege has typically full access to the system, and this is what everything which can't be handled early will ultimately trap to. The supervisor level is what your operating system kernel would run in, and then the user level is, of course, what your user space binaries would run in. And then the RISC-V community tried to define something called the SBI, or Supervisor Binary Interface, which aimed to provide a well-defined interface between these, the supervisor and machine mode. This is used to handle either operations which aren't accessible from supervisor mode, or potentially operations which are likely to vary from or where the best implementation is likely to vary from implementation to implementation, or execution environment to execution environment. And so the Linux kernel and FreeBSD port is written to use SBI calls for some key functionality, things such as setting timers for interprocessor interrupts, for remote fences. There's a basic sort of debug console implementation, as well as for functionality such as, well, shutting down the system. And so I mentioned the M mode. It's, as well as having full system access, it's also something that you would use to emulate any missing functionality. So suppose I have a system which doesn't support misaligned loads and stores, even though the user level spec says that I should, or it doesn't support it doesn't have a hardware implementation of floating point, or perhaps it has an implementation of most of the floating point instructions, but not all of them. Then you can trap those illegal instructions in M mode, have your M mode firmware implement those instructions, and then return back to supervisor mode. So it's like a very, very minimal form of virtualization in a sense. And you could view the kernels running atop of this as being minimally para-virtualized in some way. Though exactly to what extent you consider that to be the case depends on exactly what goes into the SBI interface. There have been some proposals to extend it further, so even handling things such as context switches, where the motivation would be that we've talked about having various extensions to the RISC-V ISA. Some of those extensions may introduce new user visible state. So we've certainly encountered that before when playing with extensions on the security side with tag memory. You'd want to at least swap out your tag control register on a per process basis, for our implementation at least, or you might have it for vector support or other accelerators. One of the challenges here is where does it end? In that you can implement APIs for context save and restore, but at least from our experience with, say, implementing tag memory support, it didn't end there, because we also wanted to implement support for saving those when swapping memory, swapping memory from memory to backing storage, and for actually a number of other cases as well. And so it's difficult. I think the current proposal for the SBI tries to remain very, very minimal. There are proposals to try and extend it in the same sort of way that firmware interfaces on ARM have been defined for power and clock management. And this has actually been something which has been quite a large source of controversy in the RISC-V community. So Ron Minnick, who started the Core Boot project, has written a series of well-written posts about this on a mailing list, discussing his concern about this direction, which particularly with M mode, you have a very, very privileged piece of software providing core system functionality, abstracting away the hardware in a way that the operating system kernel likely doesn't have the ability to replace, to introspect, or really have any sort of visibility at all. And this it makes it very easy to have these very potentially opaque binary blobs, which remain resident after boot, which from a pragmatic point of view, kernel developers often don't like, because they find that these blobs tend to be buggy and be a source of hassle, and it's also has potential security or, I suppose, security concerns, or a more general concern about the ability to modify and replace code on the system that you own. Virtualization is another really nice example of successful collaboration and development in the RISC-V community. RISC-V started out with the idea that as well as MS in U mode, you'd have a H or hypervisor mode above machine level, and that would be the basis of virtualization support. But Paolo Bonzini, who you may know as one of the KVM maintainers, who's very active in the KVM and QEMU community, and actually a number of other people, they fed back that actually this way was seen as has a number of downsides, and although this was actually an approach that ARM started with on ARM v7, we actually moved away later to something which was closer to x86, which is now closer to the RISC-V hypervisor extension, which was ultimately proposed by Paolo working with Andrew Waterman and others. So this effectively, rather than adding this new H mode, it adds a virtualized supervisor and virtualized user mode. And I'd encourage you to go and look up that mailing list thread or the slides for more details. But I think this is an example of where people such as yourself with expertise in a particular area, getting involved in the community, coming up with a proposal, writing it up and sending it in has actually worked really well in a case which demonstrates that there's the opportunity to have real impact. So, looking ahead to RISC-V and open hardware in general, what do we need to get rapid hardware and software innovation? From my point of view, the wish list is, well, to start with, you need an idea, or else what are you going to do? An open standard of some sort, so that there's an open and shared standard, so that there's some chance of shared infrastructure in terms of compilers, operating systems. Doing this from scratch every time is clearly unworkable. Perhaps most importantly, high quality, well-tested, or to the extent possible, verified open source implementations. You want access to something which you can take off the shelf, whether that be a software simulator or a hardware implementation, and you want some assurance that when you modify it a bit to add in your new change, if it doesn't work, it's probably your fault rather than because it's all a buggy mess that's kind of held together with duct tape. An active development community, so that when you actually start sharing patches or ideas, there's some response. It's not just going into some void. And of course, some mechanism for capturing these contributions in some way. And so the RISC-V Foundation manages one aspect of this, which is responding to proposals, discussing them. I think there's probably more to be learned from communities such as the Swift and Rust communities, who actually have a much more developed methodology for taking in detailed proposals or RFCs from community members and then applying a life cycle to look at to look at who makes the decision on those, what feedback is given, and timelines and that sort of thing. The other aspect is, of course, actually getting these changes shipping in either a future specification revision or in hardware. And with Low Risk, which is the not-for-profit which I co-founded, we're working to working towards a model where we have a regular hardware tape-out, so that when people contribute such changes, you can have some assurance that in, say, the next release in 18 to 24 months, it'll be available in some form, either produced by us or by an industrial partner who's producing a derivative design, and get that shipped back to you. Because I think making it real is important. And so I've talked a lot about the opportunities with RISC-V. It's clearly not a totally clean slate opportunity, because it's not, unless you throw away all of the operating systems and all of the infrastructure, the software that you want to reuse, that's never going to be the case. But for some market segments, there actually is a substantial amount of freedom. You don't need to rely on the Linux kernel. You don't need to rely on libc. You don't need to rely on the same design decisions which have been done before. So there'll be some cases where, because you want to make use of an existing ecosystem, you're limited in the scope of changes that you're able to make, whereas there are others where there's the ability to be much more bold. and there's no longer any limitation in terms of licensing. It's just a matter of economics and whether the relative cost of producing a software stack for those changes and maintaining that software stack over time outweighs the benefits. And of course, with RISC-V, or any instruction set architecture, we face the same challenges we've always faced in terms of security, energy efficiency, and performance. But we do have the ability to look at changes which cross all of these elements. So the ISA, the microarchitectural design, the operating system, compilers, languages, and beyond. Whereas, although there's clearly been aspects of this through previous instruction set architectures, it's always been behind closed doors. So a vendor who is maintaining instruction set architecture will take input from community members and licensees, but it's not an open process, and it's not a process which is available to anybody. So suppose you have an idea for an architectural modification. I'll have an example I'll talk through on the next slide. The steps are simply working out what changes you need to make, producing initial, it would make most sense to produce an initial prototype with a simulator, make the necessary software changes, get that debugged and working, modify a hardware implementation, testing with FPGA or Verilator. And an important step in terms of getting it out to a wider community is publishing those changes and writing it up. And this is, of course, something which has been done through academia and computer architecture research forever. But one of the nice aspects of RISC-V is that we're able to produce potentially much better evaluations and much more meaningful comparisons with existing work, because there's a range of high-quality open source RISC-V implementations to modify, rather than just trying to produce simulations based on estimating what it might look like if you were to modify an x86 core or an ARM core. As I mentioned, the pathway to inclusion in shipping hardware can be difficult, but there are multiple groups with various solutions on this. So it's either just getting it adopted by someone who's doing RISC-V stuff anyway. I mentioned Sci-5 have been doing which spun out of UC Berkeley, done a huge amount of work in this area, and their model is to try and ultimately reduce the cost of doing new silicon, so reducing the cost of new design starts. There's a whole array of other startups and orgs in that area. An example of this, which I thought was quite a nice one, was adding direct segment support to RISC-V. So this is just, I called it an optimization for page-based virtual memory. The optimization is not using page-based virtual memory. So this is where you introduce you avoid a TLB by mapping some portion of a process virtual address space directly to contiguous physical memory. And there's a paper at ISCA in 2013 which discusses this. It goes into more detail about why it might be interesting, even though you have large or huge pages. In short, you get much more flexibility in terms of the alignment and size. And this was actually really nice, because there was a paper last year which was actually by the original authors, which is where they took the idea from 2013 and then applied it to a RISC-V hardware design. And they don't hold back in terms of criticizing their previous work. They point out the limitations of the methodology they used in terms of simulation, where it was in fact producing wrong or misleading results, as it was miscounting some of the, or there was some, it was introducing some artifacts in TLB misses which were confusing things. And actually it ended up being 50 lines of modification to a RISC-V design, which was implemented in the Chisel hardware description language, and then 400 lines for Linux kernel. So a relatively manageable piece of work. Rocket is one of the RISC-V designs which I mentioned previously, which was started by UC Berkeley and now supported by Sci-5. And that's implemented in the Chisel hardware description language, which you may have heard of Verilog and VHDL. This is a sort of newer, more novel hardware description language. It's implemented as a embedded domain-specific language in Scala. One of the hopes is that it's more accessible to software developers. Whether that's, people have different views on whether it's succeeded in that aim or whether other novel HDLs have. To be honest, with low risk, we've taken a bit of a step back, and we're focusing more on traditional hardware description languages like System Verilog, as we found that it adds more complication when dealing with FPGA and hardware synthesis tools, and that it risks alienating both software developers and hardware developers. And so but some people have a very, very productive time with it, so it's swings and roundabouts. I think there's a huge amount of potential in terms of novel security solutions. With low risk, we've done work with tagged memory, which is effectively associating metadata on a very fine-grained basis. So in our case, for each word of memory, having extra tags of say 2 to 4 bits, which can be used to encode extra access control information, or for other cases where you might want to mark pieces of memory. There's a really nice piece of work from an intern that looks at the work needed to add support for that to the Linux kernel, which I guess touches on some of the issues I mentioned previously with the SBI, where you can see where if you're adding an extension which actually touches large parts of an operating system kernel, even if each part is relatively small, it's very difficult to define an ABI, a interface which allows you to abstract all that away, unless you'll ultimately end up re-implementing most of the operating system in your abstraction layer. There's an interesting story on spectrum mitigations. Of course, superscalar implementations of RISC-V have the same fundamental issue that implementations for any architecture offer, but it's really nice that we have in Boom, which is a open source superscalar RISC-V design, a full hardware implementation in order to test and explore research ideas for mitigating issues such as that. And so I think for me, the end goal is ending up with a productive and public feedback loop between really everybody involved, from application engineers, compiler authors, microarchitects, ISA designers, and beyond. And this is something which has clearly happened in smaller circles in companies such as ARM, MIPS, and Intel, but I think the opportunity with RISC-V is going to happen much more publicly in a much more mass participation way. There's no reason that RISC-V shouldn't be used as the starting point for every undergraduate learning about computer architecture design, researchers who are doing their PhD research, startups who want to take a design and modify it. And the ultimate hope is, of course, that this can lead to more rapid innovation and a much clearer path from design to real shipping hardware. And for me, the key challenges to this are, first, lowering the barrier to entry. So I've discussed a number of the barriers previously in this talk. Increasing the incentive to participate. That links back to ensuring that you have an active development community and that there's a clear story on when you actually share those changes, how do they, who reacts to that, how do they get adopted, how can you see that in real shipping hardware. And of course, there's the sort of success disaster point, which is we achieve all this, we get a really a landscape of interesting, diverse, and novel processor implementations, and how can we ensure that we maximize code reuse and sharing of infrastructure between all of these different architectures. And of course, there might be more work to do in terms of abstractions at the operating system level and kernel level in order to support that. If any of this sounds interesting to you, I should note that we're hiring. We have 7 open positions, and I'll leave it open for questions. Thank you very much.
Hi. So I'm curious about I think you barely touched on it. Yep. The difference between the sort of the implementations, like the SoCs, like the whole combined systems. So recently I've been involved with a sort of porting a certain operating system to ARM. And what we've sort of learned is what I didn't know before is that porting to ARM is the compiler actually does most of the work. The actual work is actually to support each SoC.
Yep.
So how different are what's the situation there with RISC-V? Are the SoCs as varied as in the ARM space, or are they more like the Intel world where basically everything more or less acts the same?
So I guess it's too early to say in a sense in that there aren't a large number of shipping production RISC-V SoCs. There is an attempt to standardize around cases which have been most painful in the past. So the interrupt controller was one example I mentioned, where having a standard interrupt controller does drastically simplifies the task of porting a new RTOS or operating system. For arbitrary peripherals such as UART, SPI, I2C, it remains to be seen. I hope that through what we're doing, we're trying to work on very well-specified, reusable components which people are able to use. We're able to take and adapt into their designs, but there's no requirement that people do that. So it'll be there's bound to be a diversity that we see in other architectures. I mean, look at the number of UART implementations of a Linux kernel. It's hopefully it won't grow too much, but it's just a fact of shipping hardware.
Oh yeah, those are interesting. Thanks. Linus Torvalds recently wrote about ARM and how it wouldn't be successful in the commodity server space until there was a viable desktop development environment for people to buy and have in their homes, essentially. Where do you think RISC-V is on that journey to having that?
So in the server space, so I think there's a long way to go on the server space. I mean, even with the might that ARM has had behind it and the effort which has gone on the server space, it has been a tricky path with various high-profile projects being seemingly shelved, like Centric. I think, the two paths of least resistance for initial RISC-V adoption are the deeply embedded space, so cases where people previously used sort of custom internal ISAs, and the team who wrote the compiler for it left a decade ago, and it's a complete pain to maintain. Or maybe they're using ARM and they have reasons they want to look at something else. Cases where people want to do customization of the ISA, and then on the I think the Linux capable and server side, it's perhaps a longer term goal. But there's I guess on the server space, the path of least resistance there is probably in custom accelerators, and so startups like Esperanto are working on that with cores with huge numbers of RISC-V cores and very high performance floating point engines.
Hi, yeah. Could you talk about the industry adoption of RISC-V so far, or can you buy them right now, the processor, and what does the roadmap look like?
Yep. So there's so Sci5 is I guess one of the most well-known companies who are producing RISC-V chips. So they are primarily an IP vendor, so they sell their IP and help people produce other companies produce tape outs, but they have development boards available. There's been some adoption in companies. More of it has been R&D, though you can find presentations from companies like NXP, Google, and others. It's early days. There have been some commitments. I know that there has been introduction into of RISC-V cores as sort of in a small parts of larger systems, but nothing that's yet which is both very high volume and user facing.
Okay, well, thanks very much.
Thank you.